Recording is rolling. It is Monday, January 27th. So you guys know we're starting a new topic, which is simple harmonic motion. Also throw waves in here, simple harmonic motion of waves, which actually we did start back on Thursday and Friday. So you guys know I gave you guys these spring thumbnail notes about a week ago. And if you have these yellow banners open, then that's going to be, if you want to follow along today, because mostly today what I have queued up is a PowerPoint side where I'm going to pretty much just walk through these slides, tell you guys what they're about. Later on this week, I have at least a couple other labs lined up for you guys. So if there's a spring oscillation, put a fast on a spring, pull it, let it go, wow, 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 oscillate back and forth. And then I'll have you guys calculate the speed of sound with a tuning fork and a PVC pipe. Okay. Got some other activities lined up too, but that's the main ones to look at here. All right. So think back to last Thursday and Friday. I remember you guys had some pendulums. Right? So you had string, you guys had maybe different masses. You guys were measuring angles, you guys were measuring lengths. So all this stuff was relevant. Okay? All right, and pull this back and let it go. It swings back and forth. You're trying to figure out how much time does it take to swing back and forth, right? Which would be, say, from hit my finger back to hit my finger again. Right? That would be one time period, right? Something like that. Right. And then you guys made a bunch of graphs, came up with an equation that matched the textbook equation. Everything was all good, and took off for the weekend. And all right, and yeah, now we're going back into today. All right, so today's going to be a lecture day. Mostly, I have a bunch of PowerPoint slides for you guys. Yeah, go ahead. And then, right, maybe got a couple of demos too. So here we go. All right, so here's about where I left you guys back on Friday. All right, so the time period for a pendulum. Okay, and we came up with this expression here. Right? Now you guys did 3 different experiments each. So let's walk through those, see if you guys remember the outcomes. Okay? You guys were changing this mass, this angle from the vertical, starting angle, right? And this length of the pendulum, and see how does that affect how much time does it take to swing back and forth. Okay? So, all right, one at a time. Suppose you go from a small mass to a medium mass to a large mass. If you're changing out this mass, how does that affect how much time it takes to go back and forth? And you guys found it doesn't at all. There's no relationship. You have, right? Kind of reminds me of the Galileo experiment. He's dropping small stuff, big stuff off the Leaning Tower. It all fell together, right? Because see, there's different weights, but there's also different inertias, and those effects cancel out. Right? And notice also the mass does not show up in this formula here. Right? So that's consistent with that too. Right? As long as all the mass is located in the bob, right? Once it's there, it doesn't matter how much. We are assuming that the string has negligible mass by comparison. Okay, so there's mass. How about this angle? Because what if you do 5 degrees from the vertical, only go swing back and forth, and then you do 10 degrees, and then you do 15 degrees. Right? What happens to the time period? Yeah, also stays the same. Yeah, right. Again, angle does not show up in this formula. So, okay, so maybe there's some kind of physical trade-off. Now, some physics textbooks say, well, that's only kind of true for small angles. It's what theta small. Maybe keep it less than 20 degrees. If you go bigger, it gets a little wonky, right? But it's pretty much true, right? How about this? The length of the string. Oh, guys, as you make the pendulum length longer, what happens to the time period? Does it take more time to swing back and forth? Yeah, that did. Right? That was the one variable that did matter. Right? How about this? What if you have a 10 centimeter long string and let it swing back and forth, and you time that, and then you take that to 90 centimeters, so it's 9 times the length. You guys got that? 9 times the length. How much? How many times the time period is that? For 9 times the length? Huh? It's right in this formula if you know how to read the music of this formula. Here's L, here's T. That's a what relationship? Square root? What's the square root of a factor of 9? 3. 3 times the time. So however much time it takes for 10 centimeters to swing back and forth, it's going to take 3 times the time for 9 times the length, right? You guys remember? Okay, of course, we put all those graphs together, the whole thing. And the 2 pi is kind of hard to figure out, but we did take your guys' empirical data. This worked for all my classes back last week. It said, okay, 2 pi divided by the square root of g, right, some number, right? That did show up on your graph. If we linearize that graph, there's a couple ways to linearize it. You do t versus square root of L, or t squared versus L, right? Different ways of linearizing it. But the slope of any of those graphs was consistent with exactly this equation here, right? All right. The bell rang, weekend, yay, now you're back. Yay again. So lab table. Oh, there's the graphs we were putting together. So time period versus mass. Oh, if I had a lot more time, I would see if you guys could draw these from scratch. But you guys just said, okay, for small masses, medium masses, large masses, it's all the same time. Right? For different angles, it's all the same time. Okay? Now the longer pendulums did take more time, and that was some kind of square root looking relationship. Okay? If you want to get the equation at square root, we'll use the technique we've used for a bunch of labs in this class is linearization. So if you do t squared versus L, now it lines up to a straight line. You can very easily get the slope of that line, rise over run, boom, now you got an equation, and the equation looks a lot like that. Okay. All right, everybody good, everybody good. Okay. All right, ooh, expand your guys' imagination a little bit here. So in this class, when I talk about the pendulum, we're really just focused on the pendulum where all the mass is located in this point, and the bob and the string itself has negligible mass, right? But in the real world, it's like, okay, well, what if you got something like this, like a hanger on a doorknob? You get a little tap, and it starts to swing back and forth. I mean, that's sort of a pendulum too. It's just not a classic bob-looking pendulum, right? So what's the formula for that? Now I pulled this out of a college physics textbook, but what I want you guys to see is the connection here. Because one of the things I want you guys to get out of a class like this is to see the big perspective, see what are the connections between things, or you see something that looks maybe extra complicated, say, wait a minute, actually this does boil down to something much simpler. Okay, so let's make sense of this. Now this whole hanger, this weird shape, whatever that is, definitely not a bob on a string. Okay, has something to do with this I. You guys see this capital I right here? Okay, now think back about 2 weeks ago. Guys, what does that capital I stand for? If that hanger is rotating around the doorknob? Rotational inertia. Exactly, rotational inertia. So there's some center mass of the hanger. There's this doorknob pivot point that's going around. So there's some rotational inertia, which maybe you could determine experimentally. Right. And let's connect this back to your simple classic pendulum. Like go back to this shape. Right, guys, for that point mass, because that would be kind of like a point mass, wouldn't it? What is the rotational inertia for a point mass? Does anybody remember that from a few weeks ago? What's the rotational inertia for a point mass about a pivot point? Something squared. MR squared. You guys remember MR squared for a point mass? Right? MR squared for a point mass. So let's replace this I up here, this generic rotational inertia, with MR squared for this point mass. Okay? You guys ready to do that? Okay. When I say MR squared, well, wouldn't the R for radius really be this L length, be the same thing? So really, let's call it ML squared. Okay? Guys, if I put in place of this, if you have your notes out, I see some of you guys have your notes out. If you write this out on paper, maybe it's easier to see. Right? If you replace that I with ML squared, what cancels in that fraction? Yeah, one of the L's goes away, and you still have one L left over. And also the mass, the M goes away. Right? So the M's go away. One of the L's goes away, so you have only an L on top. So you have L over G. That's inside the square root times square. Hey, that just brings you back exactly to this right here. You guys see it's the same thing, right? So that's really all I want you guys to see from that. So you probably never see the non-bob again, except right there. I just want you guys to see that. Yeah, in fact, you can make sense of that, and that's completely consistent with what you guys found empirically back on Thursday and Friday. All right. So here's your other main oscillating scenario for this class is a mass on a spring. Later this week, I'll give you guys some springs and some masses and have you guys do the full lab version of this. Right? There's a bunch of questions I can ask about this. Okay? But your two main scenarios are either the pendulum swinging back and forth or the mass on a spring going, say if you pull this down a little bit and let it go, goes boing, 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 it starts to oscillate. Okay? Now, there could be other oscillating scenarios too. So sometimes like, oh, there's an ice cube bobbing up and down in a glass of water. So that could also be oscillating, but it's mostly one of these. Okay. And guys, look at that formula for bobbing up and down. I guess I'm sort of spoiling this one, right? So this one kind of backwards of your pendulum. The pendulum lab you guys derived from scratch. This one, I'm saying, okay, well, sort of giving it away. You guys can see if this was true. You guys get these materials. Okay? It looks a lot like the formula for a pendulum. I got a 2 pi, got a square root, got a fraction. Except instead of L over G, now it's M over K. Okay, I could kind of make sense of that, right? If you know one, probably not too hard to figure out the other. Okay? How about this? Oh, guys, what if you replace this lab weight right here with a larger lab weight? What's going to happen to the time period? Does that increase or if you increase the M, does the time period also increase or decrease? Also increase. If I start with a small lab weight, it goes boing, boing, boing. I go to a larger lab weight, it goes boing, boing. Takes more time to go back and forth. Square root relationship. How about the spring? Guys, what if I replace some spring with a stiffer spring? So I got a loose spring and a stiff spring. And the loose spring takes some time to make a complete oscillation. And I got a really stiff spring. And I pull this back and let it go. Because how much time for a stiff spring? More time or less time? Less time for an oscillation, less time. But for a stiff spring, it's more like, right? Makes sense? This is exactly what the formula says too. Some kind of inverse relationship between T and K. Right? How about this? Suppose you do this experiment a couple days in this class. You're on Earth. You pull this down, let it go. Maybe it takes like a second to oscillate. Then we're going to take a field trip to the moon. So now we're sitting on the moon. And you do the exact same thing, exact same spring, exact same lab mass. You pull it back, let it go. Right? Because this is take more time, less time, or the same time on the moon. Oh. Because what's different on the moon? The moon has less gravity. Right? So less gravity, how does that figure into this equation? It doesn't. Yeah, it doesn't. It'd be the exact same on the moon. Ah, you guys see that too? I see these connections, right? Read the music of these equations. Right? How this? Because suppose you pull this down 1 centimeter and let it go. It goes, takes some time to oscillate, maybe like 1 second. Then you pull it back to like 3 centimeters and let it go. I mean, okay, so the motion changes a little bit. But what about the time period specifically? Because if you change the amplitude from 1 centimeters to 3 centimeters, how does that affect the time period? According to this formula, yeah, same, yeah, same time period. It doesn't affect it at all. Yeah, just like the gravity field. Okay. All right, so you guys good with all that set of questions? All right, work our way around that. You guys get try this out. Do the lab in the next couple days. Oh, I bet I'm going to give you a lab table that looks a lot like that. Pretty close to. We'll see. Okay, and I bet I'm going to have you guys make those graphs right there, or something like those. Right. So there's certain relationships. Maybe I'll prompt you guys to lead towards these graphs. Right. This one on the top right kind of reminds me of the pendulum lab that you guys did a few days back. Looks like you're going to linearize something that probably started as a square root type graph. Right. And then, ooh, look at this one on the bottom right. Look at this oscillation graph. You don't see too many curves like this in this class, so this is like a unit specific to, this is a cosine curve, isn't it? Right. So you guys remember like sine and cosine? Right. So as time's ticking along, this thing's oscillating. Right. Now, this could be a mouse on a spring. This could also be a pendulum swinging, like horizontal motion could make a similar looking curve. Right. All right, so next couple slides is leading into the, actually, let me flash forward a bit. Forward. Do you guys see this whole set of oscillation graphs right here? Got a bunch of sine and cosine looking curves. All right, let me go back. All right, so I'm going to lead up into that. Okay. So what if I got a couple of springs here? I got a vertical spring, got a horizontal spring. That's what I meant to mention too, but I'll fill in the blank here. Okay. You guys see this horizontal spring? Suppose I got this on an air hockey table, so there's no frictional losses, and it can just go strictly horizontally. Do you think it still follows this formula, 2 pi square root m over k? Yeah, sure does. Right. So having a gravity field or not having a gravity field, like weirdly enough, does not affect the motion of this block on the spring. Right. So whether it's vertical or horizontal actually makes no difference here. Okay. So if you watch the horizontal motion of this bottom one, so suppose you got this block going the diameter of this black circle right above it. The diameter is going right, left, right, left, right, left. You guys see that? Right. And I got the vertical one. It's going up, down, up, down, up, down. Right. Well, I bet the speed's always changing. Like slow down, speeding up, turning around, doing all correct. Right. You could describe those motions, the horizontal motion and the vertical motion, with sine and cosine graphs. I mean, pick your favorite one because they're both the same shape. You could shift them around. Right? And what that means is this: you guys see this car going around the circular racetrack at constant speed. Now he's turning the steering wheel a little bit, right? But he has a constant speedometer reading. Right? The horizontal and vertical locations of those blocks could exactly align and pinpoint the coordinates of that car as it goes around that circle. It always keeps the coordinates on the car. That's what cosine and sine is. Right? Guys, cosine, that just tells you how far right and left you are on the circle. And sine, doesn't that just tell you how far up and down you are on the circle? Right from the center? That's it. Right. Okay, so that's okay, that concept. Sometimes I see this called phase space, right? That circle. Right. All right. Another one is going to lead into the next slide. I got to define frequency, time period, and angular frequency when we get there. So frequency and time period are very simply reciprocals of each other. And I have a good auditory example for you guys. So listen closely here. You guys hear about 1 beat per second? 1 beat per second? Okay. So I'm going to call that 1 cycle per second. And cycles per second, that's a big mouthful. So there's a 1 syllable word for that, starts with an H. Does anybody know what it's called? That's a frequency of 1 hertz. Hertz. Yeah, that's it. 1 hertz. Okay. So 1 cycle per second, we'll call it 1 hertz. And the SI unit for that is 1/seconds. Okay. Now, since time period is the reciprocal of that, how much time is there between beats? 1 second. Yeah. Right. So 1/1 is 1. Right. Okay. That might be too simple. Let's do what we're fine. You guys hear about 2 beats per second? 2 beats per second? That'll be a frequency of 2 hertz. 2 hertz. And what's the time between beats? Half a second. Yeah, half a second. Right? How about, see if you guys can get this one. Is that about 4 beats per second? So that's a frequency of 4 hertz. And how much time between beats? 1/4 second. All right, let's do one more. Think maybe 8 beats per second, maybe? It looks like I'm doubling it, right? So 8 beats per second, that's a frequency of 8 hertz. And how much time between beats? 1/8 right? Okay, so that's all these two boxes right here. So time period, frequency, or reciprocals. Guess that. Okay? Because what if I kept doubling? Do you think at some point it's going, your brain kind of loses track of the individual beats and starts to sound like a low hum, like, you guys think? And if I keep turning it up, think about like a rising tone. Okay, so your brain has lost track of the beats now because there's like hundreds of beats per second. Now you hear, hey, is that what music is? Is that musical notes? Okay. Does anybody? Somebody might know. What's one of the A notes defined as? One A note could be defined as how many hertz? 440. Oh, actually, I was saying that somebody knows. That was kind of a lie. I didn't think anybody knew. Nobody's known that all day. But these knows. Yeah, 440 hertz. 440 hertz. That's it. Right. So if you had 440 beats per second, you would perceive that as an A note. Right. Right. And so more on music later. Okay. So back to I gotta lead back to these graphs though. Okay, so here's your two scenarios. Basically, we're talking about pendulums and blocks and springs. Okay. All right. Here's another type of frequency. Guess use Greek letter omega. Now, careful. I know a few weeks ago we were using this Greek letter omega to talk about angular velocity, which is like how fast is a turntable turning. Right. That's not what it means in this context. I mean, there's only so many letters. Run out of Latin letters. Run out of Greek letters. Start recycling these things. In this context, it means angular frequency. All I'm doing is I'm taking the regular frequency, so 4 hertz, 8 hertz, 440 hertz, whatever. I'm multiplying by 2 pi, and that's going to help me construct the graphs on the next slide, okay? Because, guys, how many radians are in one complete circle? 2 pi? That's where that comes from. That's the connection, because that's how you can identify one complete cycle. All right. I think we're ready for this one. You guys ready for this one? Okay, now this one, there's some things I want to point out by hand. So this one, I better have the physical version right here. Right, let's get this going. Okay, so let's make sense of these. So remember, here's the physical scenarios. Either you got a pendulum swinging back and forth. Maybe you want to see what is its x location horizontally as it swing back and forth from the center line. Or you got a mouse on a spring bobbing up and down. Say, what is its vertical position? Either of those could be described by these graphs. Okay? And what graphs are we looking at? Well, look at, see, position versus time, velocity versus time, acceleration versus time. Hey, it's the same 3 graphs that you guys saw last semester over. You guys remember kinematic days? X versus T, V versus T, A versus T. They're back. They never went away. Okay? Now we're just looking at the oscillation scenarios, right? Right. So one complete cycle right there has somehow described that. Like, what's the basic function to describe this wave-looking shape? Well, it's either sine or cosine. And again, sine and cosine are the same basic shape. You could kind of shift them around and overlap them exactly, right? So you could either start with the sine or cosine. Now, I prefer to start with cosine for this reason, because if you start with cosine, you get this intercept here, which implies that you're starting with some displacement. Well, you are starting with some displacement. So like last week, you guys pulled this back. So with some initial displacement, and then you let go. Okay, so it gets kickstarted like that. Okay. All right, so I'll start with the cosine. Okay. All right. All right, and then if you want it to cycle all the way around once, like there's one full cycle. Okay. Okay, suppose that was 1 second. Can you guys imagine if that could be 1 second, like 1 second per second? Actually, the second hand on that clock, tick tock every second. Let's say every second it cycles right there. There's one full cycle. Okay. Well, how would I build that to the equation? Because I know that a cosine function cycles around every 2 pi radians, and if this is in radians, okay, that's this connection right here. You guys see this omega? Remember, this is not angular velocity. This is angular frequency. That's what I'm talking about. Okay, so 2 pi times a frequency of 1 hertz, because I'm talking about 1 hertz, right? Okay, okay, that's what pops in right here. And then this t is a variable, so I'm just letting time tick along. You guys see that? Okay, so if it's a frequency of 1 hertz, then times 2 pi, that means every 1 second, it completely cycles around. Aha, see that connection? Okay. Okay. Oh, how about this A right here? Guys, what do you think this A stands for? Amplitude, amplitude. Okay. Suppose this was like 5 centimeters and you change it to 10 centimeters, so you double it. Guys, if you double this A, how does this graph change? Yeah, it gets taller, it stretches vertically. Okay. So if this was 5 centimeters, that would stretch all the way up to 10 centimeters. The 0 would stay 0, and this -5 might go to -10. Like it could be stretched vertically, wouldn't it? Is it? Okay. Let's talk about rates of change, because you're seeing 3 graphs, and that's the connection between them. Rates of change. Right. So, guys, what's the physics? Let's make for sure everybody knows what I'm talking about. Guys, in physics, what is the rate change of your position called? The rate change of your position is your velocity. So if you're changing 60 miles an hour, sorry, if you're changing 60 miles every hour, your velocity 60 miles an hour. Okay. What's the rate change of velocity called? Acceleration. So you guys see these graphs are rate changes, right, as you go down, right? Right. And rate change on a graph is really the slope of the graph, isn't it? Slopes turn into coordinates. Right, so can you guys just imagine if I had a hilly terrain? You guys see a hill and a valley and a hill and a valley and a hill, and I'm like walking left to right. So I'm walking up a bunch of hills and valleys. Right. Right. So right now I'm standing on top of the first hill. You guys see how I'm holding my ruler flush to the curve? Now, guys, if you're standing right on top of the hill, what's the slope of the curve at the top of the hill? 0. 0 slope. You guys see 0 slope? It's level for only 1 point, but it's level, right? Guys, if you have 0 slope, 0 rate change at that 1 point instantaneously, right? Doesn't that correspond to the rate change graph being 0? Okay, that's why the slope of x versus t tells you the coordinate of v versus t. I mean, it's the same story as last semester, right? But now we just got the oscillation version, right? How about this? I'm starting to walk downhill. Guys, if I'm walking downhill, I'm holding my roller flush to the curve. Ooh, what kind of slope is that? Positive or negative? Negative, which means that the coordinate of v versus t, it's negative. Look at that. Right? In fact, as I'm walking downhill, isn't it true? The slope is getting more and more and more negative. It's getting even steeper and steeper and steeper. And this coordinate's getting even more and more negative, right? Until you get this point right here. Guys, at this point right here, have I maximized out the slope? Right? It's probably really hard to walk down that part of the hill because it's so steep. That corresponds to the maximum negative coordinate, maximum negative velocity. Okay? And once I pass that point, am I still walking downhill? Am I still walking downhill right here? Yeah, but it's not as steep, is it? Right? And then, okay, and down here, it's still a negative coordinate, but it's tending back towards 0. Ooh, right? And then when I finally get down to the valley, guys, down here in the valley, what's the slope of the valley, at the bottom of the valley? 0 slope. That corresponds to 0 coordinate on v versus t. You guys see that? Right, now, of course, instantaneous. It's always on the move. But, okay. After I pass the valley, and now I'm just starting to walk uphill. Guys, uphill is what kind of slope? Positive or negative? Positive. That corresponds to velocity versus time being a positive slope. Like I said. Okay. In fact, it's maximum positive slope right at this node point right here. Guys, it maxes out positive. Corresponds to this point right here. And after that, I'm still walking uphill. Right? And then it goes to 0 slope at the top. Corresponds to 0 coordinate right here. You guys see that? That is the translation. Now, guys, the mathematical process that I just walked you through is what branch of math? Calculus. That's calculus. We just walked through some calculus. It's calculus about rates of change, right? Okay. In fact, if some of you guys have taken calculus, I bet you guys know. Let's try this back to the formulas: sine and cosine. What is the? Let's start with sine, and it's a little bit weird in the middle. What is the rate change of sine? The rate change of sine is called what? Cosine. And what's the rate change of cosine? Sine and also negative. So you can go from sine to cosine, and cosine turns into negative sine. That's why from here, this cosine to this sine also ends up with a negative sign. Right? Let's go from this one to this one. Okay. It ends up being a four-part process. Sine here. I should really map this out. Okay. So if you're looking at rates of change, right? It's this four-part process. If I start with sine, let's say sine of t, the rate change of that is cosine of t. The rate change of that is negative sine of t. And the rate change of that is, well, sine cosine cosine, so I already have the negative, so that'll just stay there, right? And then the rate change of negative cosine is positive sine. You guys see it's this four-part loop, and it could just loop forever. Is that right? Right. Speaking of four-part loop, I see rate change of x is v, rate change of v is a. Because what's the rate change of acceleration called? Did I mention that last semester? I might not have. Does anybody know? It's called jerk. It's called jerk. Right. And anything that's oscillating, you guys see, like in theory, you could just sort of take rates of change forever. Okay. Okay. One last thing to round this out. Let's bring in this omega right here. You guys see this omega, which is angular frequency, 2 pi f. Okay. You guys see every time I take a rate change, I get another omega that comes out front. Right. So it wasn't there to start with, and I get one here, and then it gets squared here. I bet the jerk version would have omega to the power 3. You guys see that? And so on. Right. In calculus, that's called the what rule. Starts with the ch. Called the chain rule, right? Something like that. All right. Okay. So that's a lecture. All right. Let's go back to PowerPoint. You guys good so far? Good so far? All right. So we look at rate change. Right. Oscillation linearized. Of course, the graph on the left we did back on Friday. The graph on the right, I bet you guys are going to see later this week for a little bit different oscillation scenario. I bet you guys can oscillate oscillate a mass, make a graph. Empirical data. All right. This one's a little involved, but I want to walk you guys through this anyway, so you can see an interesting connection here. Okay. So I'll probably have you guys do this anyway. So suppose when I give you a spring, you hang the spring from like a ring stand. It's there. It's just hanging vertical. Right. Nothing on it yet. Okay. And then you put a lab weight right there. You hook on lab weight. Everybody got that? Okay. And then you let it go, and it's going to overshoot the equilibrium position and stretch to some maximum stretch position. Right? And it's going to oscillate for a while. Right? And then maybe after a long time, dampening and frictional losses, it eventually comes to a stop at equilibrium. You guys see that? Okay? Guys, look at this equilibrium stretch position and look at this maximum stretch position. Are those the same or different? They're definitely different. If I got my animation right, if I got this picture right, guys, they're different by a factor of what? What is x max compared to x equilibrium? It's off by a factor of 2. You guys see it's like twice as much, right? Now, how can you show this? One way you can show it is empirically, right? So when I gave you guys all the lab materials, you can try this out yourselves and see how close to true this is. Should be pretty close. Okay? But what about in terms of textbook formulas? So let's talk about like a textbook way of proving this. Okay? Let's start with equilibrium. Right? Guys, to show something is in equilibrium in physics, what's the equilibrium condition? The sum of what goes to what? Sum of forces goes to 0. Yeah, sum of forces goes to 0. Okay? That's my framework right here. You guys see that kick starts off this process right here? Sum of forces goes to 0. What forces? Well, I got the weight pulling down. I got the spring force pulling up. Hey, look who's back. It's Hooke's law. F equals kx. Yeah, you guys see Hooke's law? Right? So those subtract out to 0. I can solve for x equilibrium and get this expression right here. Okay, great. I got that. The more weight, the more it stretches. The stiffer the spring, the less it stretches. That all looks good. All good? Right. Now, if you want to solve for, wait a minute, I remember when I first dropped it, it overshot that position, went to some maximum stretch. Right? Because what framework do you think you need in physics to solve for the maximum stretch? Not equilibrium. It's definitely not equilibrium. It's what? Conservation of energy. That's this right here. Right. You guys, what type of energy at the very top? Right when you're hanging on the lab weight, it's what type of energy? Gravitational potential. And at the maximum stretch point, where'd all the energy go? It went into the spring, right? That's why I got set up right here. So I got an mgh, turns into 1/2 kx squared, right? And if the h is also the maximum stretch height above the lowest position, sub that in, right? Anyway, you solve for that, and here's the maximum stretch length. Now compare these two gold boxes. You guys see these two? Okay. They look really similar. Both fractions, got the mg, they got the k. Okay. The only difference is this factor of 2. Is that? Okay, so prove that one. Okay. So it's a little more involved, but yeah, come on, think about it. All right, guys, good so far. Good so far. All right, so that's a bunch of simple harmonic motion, oscillation type stuff. Okay, let's go on to waves. Right, so there's definitely some crossover content with waves. They both have a time period and a frequency, oscillating, will do. Right. Let's look at properties of waves. So what if I have a standing wave? Now, not all waves have to be standing waves, but it could be. What if you shake up a rope up and down so that there's these nodal points that emerge? I might do this as a demo one of these upcoming days, but today's just a PowerPoint day. Right? Okay. And then if I got these green nodes, then, well, these red points could be antinodes. So they're just moving up and down. So the whole thing's just moving up and down. Right? Now, there might be some energy propagation, but I'll talk about that in a few minutes. Right? What's the shortest part of this wave where you can go point to point and you could cut it out and copy paste it next to itself so that it repeats? Could it be this crest here to an adjacent crest right here? Yeah. And I'm going to call that one what? One wavelength. One wavelength. Right? And the character for that is going to be this Greek letter lambda. Okay, so lambda, one wavelength. Okay. Now, you don't have to go crest to crest. You can go trough to trough. You can go one of these nodal points and skip a point and go to the next nodal point, make a full S shape. Right? That can do it too. Right? There's different ways to measure it. So it's all the same length though. Wavelength. Right? Okay, we've got frequency, time period, and reciprocals. Got that? Oh, oops, I almost missed this. Guys, what do you think this A stands for? Amplitude. All right. Good deal. All right. All right. Maybe well, if this was a sound wave, which is actually a longitudinal, it looks a little different. Maybe it could sort of represent how loud is it. All right. All right. Guys, look at this formula down here in the bottom right. You see V equals lambda F? Great. Make sure you guys know what you're reading. I think you guys can put this together. What do you think the V stands for? Velocity. Okay, like velocity, like the wave speed. There's the wave speed, velocity. Okay. What do you think the lambda is? Wavelength. Right. What do you think the F is? Frequency. Right. Like I was just playing that sound file, like so many hertz, so many cycles per second. Right. Back when I was in college, I was majoring in civil engineering. I had some classmates who sort of remember this formula, but couldn't remember exactly how it went together. Like, okay, I know there's a speed, there's a wavelength, there's a frequency. I don't remember how to do that. All right. One of the things I want you guys to get out of this class is, even if you don't like rote memorize this, you can figure out how to put this back together if you know how things work. Right? Let's think in terms of units. You guys ready to think in terms of units? Guys, what is the unit for wavelength? How could you measure a length? And what unit? Meters. Yeah. What's the unit for frequency? Hertz. And hertz is like cycles per second, isn't it? And we're going to call it 1 over seconds. Put it all together. Guys, what is meters times 1 over seconds? Meters per second. Hey, and that describes the speed, doesn't it? You guys see how that all goes together? All right. And now there's no way you can forget that. Because even if you do, you can just piece it back together because now you know how things work. All right. So there's usually considered to be 2 main categories of waves. Some textbooks have other ones, but I'm just going to focus on these 2. So transverse waves versus longitudinal waves. Now, what's the difference here? So if something's transverse, then the motion of each individual particle and the propagation of the energy are usually perpendicular to each other. So I'll show you guys a video demo here in a minute, but okay. Suppose you have, I don't know, a rope, a slinky, whatever. I'll show you guys a slinky video, right? Where you're shaking the slinky up and down, and each individual particle only ever moves up and down. But you can watch the energy propagate left to right. You guys can see that? Or how about an ocean wave? Do you guys see like the ocean waves coming in on shore? There's some propagation of energy that's like horizontal, like moving from the ocean towards the shore. But the individual water molecules pretty much just move up and down, pretty much, right? Now, of course, when it gets to the beach, right, they'll move horizontal a little bit. Okay. Yeah, let's grab this one. All right. Now that's different than, you guys see this bottom wave called longitudinal? So longitudinal wave is a pressure wave, and here the motion of the particles is parallel to the propagation of energy. So the particles move right and left, and the energy might also move like left to right, propagate across in the same direction. Right? How do you guys think you're hearing me right now? What do you think a sound wave is? Transverse or longitudinal? Longitudinal. It is. It is. Right. So if you could see the air molecules between me and you, watch my voice carry. Okay, and you could like you'd see these high and low pressure points oscillate. Right. So like sound needs a medium to travel through. Oh, okay. So can sound travel through the vacuum of space? No. Right now, light can because light's a transverse wave. Electromagnetic works a little different, but sound is this pressure wave down here. Okay. Now, a longitudinal wave, if you draw a proper longitudinal wave like the one you're seeing, that can be really hard to draw because you have to sit there and like dot, 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 and draw a bunch of dots with your pencil. And then you got to stand back and say, okay, did I get like the density of the dots correct? Or the space correct? All right, so it can be kind of hard. It's really common to represent longitudinal waves as transverse waves, even though they aren't. So, because the transverse wave is so easy to whip off. So just kind of be aware of that. If I'm talking about sound waves, and I whip off a transverse wave, it's not really transverse. It's actually this bottom line. Okay, guess what? All right, all right. Let's look at some demos. All right, we find. There we go.
Now, you might be wondering, is light a transverse?
Ooh, do you guys see transverse? All right. So you guys see each individual particle is just moving right and left, but the wave energy is propagating towards the back of the video. Ooh, there's transverse.
Or a longitudinal wave?
Ooh, you guys see those nice longitudinal waves? In that one, everything's moving in the same direction. The individual particle motion, points in the slinky, and the energy. It's all moving in the same direction.
How could we test this? This device is called a polarizer. It's designed to let waves get through in only one direction. As I send the wave out, it gets through fine that way, but this way, I can't get the wave through. No matter what crazy wave I send, only the left and right components get through. It's been polarized. Now that only works on transverse waves. If it works on light, then light is a transverse wave. Because light can be polarized, we know it's a transverse wave. This is a polarizer. It's polarizing up and down. This is another polarizer. It's polarizing left and right. When these two are crossed, we get absolute darkness, zero transmittance. But if we cross them the other way, light still gets through. They're polarizing together the same way.
Yeah, you guys see that right there? All right. So just by turning it 90 degrees, you can cut the light out or let it through. Right. I know I have some polarizing filters that I think I have to dig them out, see if I can find them. But if you have some polarizing glasses and your friend has some polarizing sunglasses, you could do this exact same thing. Right? Or say you go to the store and there's like a whole rack of polarizing sunglasses. Try this out. Take a couple of pairs and rotate them like this. At 90 degrees, it'll all cut out. So it's an example of light being specifically a transverse wave, right? Because that only works on transverse wave. Light's an electromagnetic wave. Okay. Transverse. All right, constructive destructive interference. Say you got a couple of wave pulses headed toward each other. What happens when they overlap? Right. Well, or does it matter if they're right side up, upside down? Let's look at a couple examples. Start with constructive. There we go. So you guys see those two pulses right there? Whoops. There's 7. Suppose they're going, all right. They're like 5 centimeters and 5 centimeters amplitude. They cross and they make like 10 centimeters. Woo! See how they add up? And they also just continue crossing through each other. So the energy propagation just keeps going. Okay. So there's an example of constructive. Let me find destructive. Destructive. Okay, now there's a lot going on in this one. Right, you guys see this rope right here? So I might pause this a few times and go back and replay it. All right. Okay, I see a couple of pulses. You guys see a positive pulse and a negative pulse? Is that they're headed towards each other? Because what do you think is going to happen when those two pulses cross over each other? Huh? Let's see. Hey, look, they flattened out. They flattened out. Okay, is that it? Do you think that's the whole story? Or do you think something's still happening? Let's see. Oh, look at that. The energy just kept going right through. Okay. Also, the tail end, this is a little extra detail. Do you guys happen to see that this wave actually reflected upside down? All right. And watch this one. This one's still about to reflect the other way too. Let's see if it does. Hey, it did. It reflected upside down again. All right. Here, I'll go back and replay the whole thing one more time. All right. So here's the whole thing. So it's two pulses, one up, one down. Now they sort of cancel when they cross each other, but then they just keep on propagating. They go straight through each other. Go straight through. Huh, that's pretty cool, isn't it? Okay. But that point where they cross over and they're canceling out just for a moment, that's an example of destructive interference. Okay. Guys, who's ever worn noise canceling headphones? Noise canceling headphones. Okay. That is also an example of destructive interference. Now, of course, that's for sound, which is longitudinal, but it's the same principle. So how those work is the noise canceling headphones. Now you have to turn them on. They're probably battery operated, aren't they? Okay. So they'll take the ambient sound from the air. They'll analyze what's all the high and low pressure points, and they'll swap them, and they'll mix it with that ambient sound. So what gets pumped into your ear is just like pure silence, right? Once you cancel out all the positive and negative. Okay. All right. So else I got? Ooh, interference pattern. So there's a famous experiment called Young's double slit experiment. He took a card and shone light through a couple of slits and made this interference pattern to try to show what the nature of light was, right? Like, is light fundamentally a wave or fundamentally a particle, right? Like, one question that's been around for thousands of years is, like, what's the nature of anything in the universe, right? Like, when you get down to it, what is everything made of fundamentally, right? Now, of course, nowadays we have the atomic theory of matter. You say, oh, okay, well, I took chemistry last year and I can point to the periodic table and everything's made of atoms that look like those on the table, and right? But people didn't know that until relatively recently. If you go back to like Isaac Newton's day, just a few hundred years ago, say like what is light? Is light fundamentally particles or fundamentally waves? Right? And how can we define what's what, or what is anything for that matter, right? So usually everything's considered, categorized one or the other. Now, when we get to quantum, it gets really weird because now there's weird gray zone. But if you can get this interference pattern, say if you have a card and a tank of water, just let some ripples go through, right? It'll get these points of periodic constructive destructive interference, get an interference pattern that tells you, okay, you're probably working with something that has these wave properties. So I can put it into category waves. All right, it's got that. All right, guys, get a good look at this one because this is going to be a lab you'll do later this week. I'm going to have you guys calculate the speed of sound with this method right here. So I got a box of tuning forks. Strike a tuning fork. It's like some musical note, something like that. Now it'll tell you it's got a frequency stamped on it. It might say like 440 hertz. Okay, I guess I must have an 8 for my tuning forks. Okay. Then I've got some PVC pipes and some tanks of water. You guys see if you take a PVC pipe and you dunk it in a tank of water, you guys see that's this right here, isn't it? Right? Okay. And then you hold the tuning fork above that. And then you raise and lower that PVC pipe into the water. Well, the water level will effectively close one end, and the top of the pipe is an open end. And there'll be some points where it resonates. And those are exactly the pictures I have here. So here's what it sounds like as you're raising and lowering the pipe into the water with the tuning fork. It sounds like this. And where it's resonating, well, you either have this picture on the left or this picture on the right. That's what it's going to be. Now, the proper longitudinal wave is like all those little dots are there. You guys see a high pressure point right above the water? Right? And for this next picture, the high pressure point, about 2/3 of the way up to the top. Right? And there's low pressure points. Now, the easy way is just to whip off transverse looking waves. And that's what the little S curves are about. Right? But it's really, okay. Just to get the idea. Okay. All right. So say if you could put this together. If you know the frequency right off the tuning fork, okay, I know what musical note I'm working with. And you can figure out the wavelength. And I bet you could do it this way. You could take the length on the right side, the length on the left side, subtract those two, go from here to here. That represents half of the wavelength. Here, let's do some numbers. Because what if the pipe on the right side is 30 centimeters long and the pipe on the left side is 10 centimeters? Guess what's 30 minus 10? 20, right? And then if you double that, that brings you to 40. So I could say the wavelength of that wave is 40 centimeters. Right? Combine that with the frequency on the tuning fork and see if I go back a few slides. Right here, right here. You guys see this one? If you know the wavelength and you know the frequency, can you put that together and get the speed? And we're talking about the speed of sound is what we're talking about. Speed of sound, right? So that's what it looks like resonating for one closed end, one open end. If you guys ever blow into a bottle and it resonates, blow into a glass bottle, something like that. Right? Yeah. How about what if there's a pipe open at both ends? Right? Maybe remember seeing an AP question in the past where there's like horizontal pipe and there's like wind blowing through, right? Something like that. Right. You get these low pressure points on the open ends, both open ends. Right. Something like that. Okay. Here could be well, I don't quite have this equipment, but right. You can set up different standing weight. Actually, I think I have a video. Let's see. I think we got an extra minute in here. Let's see if we can dig up this demo. Ah, here it is. So you can actually see this in motion. Uh, Here we go. Right. So setting up some standing waves on this string. So he's got an oscillator on the right. Well, sorry, oscillator on the left side. Okay. Bounce up and down. Okay, so this is some kind of wave propagation. All right. It looks like, okay, 11 hertz. It sets up that type standing wave. Fast forward a little bit. Here's 22 hertz. So if he doubles the frequency, ooh, see it like double the number of lumps. Okay. Now that right there actually is one complete wavelength. So go back to the beginning. There's half a wavelength. Right, there's one wavelength. All right, and then there's 1.5 wavelengths. You can see, got 33 hertz. Looks like every 11 hertz, it's hitting another standing wave, right? Now, some of these, it doesn't create a very clear wave, but then, sometimes one will pop out. Well, 44 hertz. Oh, surprise. There's two complete wavelengths. That's two complete S shapes, two full wavelengths. Guess that? All right, so here's a little video demo. Okay. So it looks like that right there. Okay. Let's do a little bit of music stuff. So if you play any kind of stringed instrument, this could be guitar, violin, a piano, right? Maybe you have to tune those strings at some point. So you have a tuning peg, you make the string tighter and it sounds like a higher musical note, and then you make it less tight. Okay, you're looking for like a specific musical note. Okay? What's the physics? Okay. So here's the formula. So I know the speed of a wave on, say, a string could be the square root expression. It goes like this. So square root of, okay, got tension, like the more tension, the faster the wave propagation. Okay. And then divide by the linear mass density. So the mass per unit length of whatever string I'm working with. Okay. So there you go. Okay. Okay. Well, where's the musical note in that? Not quite there. So I'll do a little substitution. Well, I know this wave formula, speed equals wavelength times frequency. And for this standing wave, well, just from that video demo, I just showed you guys that standing wave is half of a full wavelength. So twice the length would be the full wavelength. Right. So substitute right there. Right. And here's your connection. So if you're targeting, say I want to make this like a G note, right? So that could be so many hertz frequency. Right. And then you can figure out exactly how tight to make that string, the tension. There you go. That's a connection. All right. Lab stuff. All right. What is the relationship from musical notes? So there's a story, it goes back thousands of years. I think it was Pythagoras, was walking along the road one day. There were a bunch of craftsmen like hammering out pots, just making pots. And he was listening to them hammer, and he was listening to the tones that were created. He was, oh, hold on, it sounds really good when you hammer that pot and when you hammer that pot. And then so then he starts measuring the diameters of these pots. It's okay. Well, this is like well, they didn't have meters back then, but just get the idea. Okay, this is 1 meter diameter. This one over here is 1.25 meters diameter, and those sound really good together. Why is that? And he starts measuring a bunch of pot diameters and say what ratios of these diameters sound really good together. Right, it comes up with these musical note ratios. Right, so here's the end of this. Here's the tail end of this. So every musical note, there's some corresponding fundamental frequency. Maybe like A could be 440 hertz at some point. Okay? If you double that frequency, so double 440, that could be 880. It's the same musical note, but it's a different octave. You could go the other way too. So 220 hertz is also an E note. It's just one octave down. Okay? And then what about all the other notes on the scale? Well, they'll have some frequency ratio relationship. So if you have a 3-to-2 ratio, that's the perfect fifth. If you have a 5-to-4 ratio, ends up giving you a major third. If you play all these together, you create a major chord, right? You see a major chord, and of course there's a bunch of other ratios too. I'm just showing some of the main ones for a major chord, right? You guys see this green box here that says equal temperament. So this is like a modern modification of this. If you go back hundreds of years ago, let's say you go back to like Beethoven's day. When Beethoven played a piano, I don't think it would have sounded like a modern day piano because there would be some preferred key that everything would be tuned in terms of. And there are different tuning conventions, but I'm showing the Pythagorean ratios right here. And when you switch keys, well, you get slightly different tonality. So sometimes composers would suggest like, oh, if you play in this key, maybe you'll get like a happy sound, and play in this key, you'll get like a melancholy sound, or play in this key, like a nostalgic, or no. That doesn't really apply today because today instruments are tuned according to equal temperament. You guys got a calculator out? Calculator? Try this out. We're gonna try this green formula. All right, I want you guys to see this. So let's say root node is whatever number. Type 2 to the power of, you guys type that, 2 to the power of, then open parenthesis. Okay, now let's hit this major third, which is actually 4 half steps above the root. So do 4/12. So do 2 to the power of 4/12. You guys just do that? right? Now, when you hit enter, I bet you get something close to, but not exactly 1.25. Is that right? Get something close to, but not exactly 1.25. Right. Here's why. That's supposed to approximate this major third, but it's not perfect. Right? Um, the trade-off is like the advantage of equal temperament is that you can change keys within a song and everything sort of sounds the same, right? So like, so whether you're playing in the key of A or G or C or whatever, that doesn't really make a difference. Right? All right, so I'm actually showing you two different conventions on the same slide here. Right? All right. Doppler effect. You guys ever stand out on the road, a car goes by, so it's like, meow, right? Something like that, meow. Or hear the ice cream truck go by, you're playing a happy song, and then it sounds super eerie for a moment. Right? So pitch shifts. Now, how you perceive a pitch shift, or this talking about the Doppler effect here. All right, we'll do more on this another day. Got a couple minutes here today. Depends on where you're standing. It has to do with relative motion. If you're in the car, you don't hear it at all. If you have a whole line of say 100 people along a sidewalk, as the car goes by, everybody hears something a little bit different. And so we'll do this one day, right? So what does this pitch shift have to do with how fast the car is going, whether it's going towards you, away from you? Can you do these calculations? So say that for one day. Okay. Ooh, guys, do you think this car could go faster than the very waves that it's sending out? Yeah. Would that be called supersonic? Super greater than sonic sound, supersonic? Ooh, right? And that's what Mach number is, right? Like if a jet's traveling Mach 2, it means it's traveling twice the speed of sound. Right? So what's the speed of jet compared to the speed of sound? Pretty much, right? Yeah. All right. Do you guys ever hear a sonic boom? Sonic boom? So if you ever hear that, what you're hearing is the front of this cone wave hitting you. So you're sitting right here, you watch a jet or a rocket go over, whatever, right? And then once this cone wave hits you, bam, that's the sonic boom right there. Right? All right. Oh, here's the last slide today. All right, so last slide is lecture stuff. How can you quantify how loud something is? So this is called sound intensity level. I'm going to quantify that in decibels. Okay. Now, decibels works on a logarithmic scale, or you can say exponential, two sides of the same coin. So if you want to double the loudness of something, you don't double the number of decibels. Actually, doubling the loudness of something, it's almost exactly 3 decibels, I think is how it works out to. Okay, so say like some speaker is on, you want to double that loudness by having 2 speakers. They might jump up from 60 to 63 decibels, something like that. Right? So it's a log scale. Anyway, there's some formulas here. We may or may not get to navigate in these formulas, but at least I want to give you guys exposure to what that is, and it's on a log scale. All right. All right. I think that's a good pause point today. All right. So look for a couple of labs lined up pretty soon.